change. Up to this point, everything we've been talking about in this class has primarily been weather related. But in this module, we're going to go to what is really considered one of the biggest issues, one of the biggest topics, one of the biggest concepts that is really being talked about in the media today, in politics today, and I'm sure you've heard the word climate change everywhere. And so that's what we're going to be talking about today and in this particular module. And this module is going to be broken up into 5 main components. First, we're going to talk about the concept of climate change. So what is climate change? How does it differ from global warming? Why do we use the term climate change? Then we're going to talk about the context of climate change, and that's really breaking down the whole idea of how is our climate changing? Is it natural? How do we know that our climate's changing? How can we compare it to the past? Then we're going to talk a little bit about the causes of climate change, both natural and man-made. Then we're going to talk about the consequences of climate change. So why is this so bad? Why are we concerned about this? And then we're going to talk about what we're doing to fight climate change in a sense. So first off, why should we even talk about this? Why is this something that's even worth being taught about or being talked about, being covered in this class? I mean, this is a meteorology class. So why are we even talking about climate change? Well, for me personally, the biggest reason why I see this as an important topic to cover is that there's a lot of misconceptions out there about climate change. The first thing the key point that I'll make here comes from this comic. This is something I found on a political, I'm not going to say which party, a political Facebook page. And what it deals with is it deals with different terms that have been thrown around in the past. Global cooling, global warming, climate change, climate disruption. Are we getting warmer? Are we getting cooler? And there's this confound scientist. And then beneath all of these potential terms, there is a very poor definition, if I may say so myself, that says dramatic changes in temperature and in the state of the atmosphere. Meanwhile, over here, there's a little smart aleck 5-year-old boy that writes, it's called weather. And one of my hopes is that by this point in the course, you've had a pretty good sense of the difference between weather and climate. So what is climate change versus what is typical day-to-day weather change? But the reality is that there's so many misconceptions about global climate change, about the terminology that we use, about the politics behind it. And the fact of the matter is that a lot of people aren't talking about it, or the wrong people are talking about it. So rather than hearing from some of the top scientists in the world like Richard Henson or Warren Washington, instead we're hearing from politicians like Al Gore or celebrities like Leonardo DiCaprio. And that gives a real misconception to the truth behind climate change. And so that's one of the reasons why it's so important to talk about it. There's a lot of misunderstandings, a lot of politicalization, and therefore a lot of people automatically tune you out. And so just to forward everything else I'm going to say in this module, I'm not a politician, I'm not a celebrity, at least I don't think I am. And so I do, however, have an understanding of climate change and the science behind it. And I have actually worked on a climate model, and I have actually seen much of the climate change research being done. And so hopefully sort of taking the political side away and taking sort of the celebrity side away, I can give you a good understanding of what's actually going on. So first off, let's actually talk about what climate change really is, and what it's not. So here is a good definition for climate change, and the definition that we're going to use in this class. Climate change is the reaction of our atmosphere to what we have done to it. to what we have put into it. And so when we talk about climate change in this class, we're specifically talking about what's called anthropogenic climate change. The reaction, the change of our atmosphere, the change of its composition, the change of its energy balance to what we have done to it, how we have changed it. Now, until about 20 years ago, the popular term that was being used was called global warming. Here's the problem though. The problem is that not every region is experiencing warming, and not every region is experiencing the same amount of warming. And you can actually look on a map of temperature anomalies for the last 5-6 years, and what you would actually notice is that some locations are even experiencing cooling. A good example of this is locations near the coastline. Most locations near coastlines have actually been experiencing cooling over the last 100 years. And the reason why that is interior regions have been experiencing warming. We know that warming creates a stronger temperature gradient, which creates a stronger pressure gradient. And if you recall from our module on wind forces, pressure gradient creates wind. And so sea breezes have been enhanced because of this. That has forced more ocean air to be pushed onshore, causing cooler afternoons. So that's one example of a location that isn't experiencing warming. The other reason why we've thrown out the term global warming is it's very easy for people to think that climate change is just warming. And so on a snowy day or on a day where record cold is being experienced, it's so easy for somebody to make a pseudoscientific claim that, okay, well, hey, it's snowing outside, therefore global warming is not happening. Therefore, this whole thing's a myth. And so global warming is a very misleading term. And that's actually something I really want you to get from this module, is that global warming is a misleading term. Because not everywhere is experiencing the same amount of warming, and not everywhere is experiencing warming at all. And as I just mentioned, a good example of this, coastal regions have been experiencing cooling. So with that said, that's the concept of climate change. The idea behind climate change, the concept of climate change, simply comes from the fact that not every region is warming, and not every region is warming the same amount. With that said, the global average temperature has increased. And I think that's why the term global warming used to be such a popular term. Because when you look at that one variable, global temperatures have increased. But we'll actually talk a little bit about how this looks like as we uncover the context of climate change. So let's do that. So the first thing we need to understand when talking about the context of climate change is how has our Earth's climate changed over the last 100 years, 150 years, and how does it compare to previous climate shifts? And in order for us to do this, we need to compare recent climate changes to long-term climate changes from centuries, millennia, many millennia ago. And then if what we're experiencing now is way different than anything experienced in the past, then we can be a little bit more sure that, okay, this is a big issue, this is something we need to be worried about. So in order for us to really get an idea, we need to look in Earth's past. But how do we actually do that? How do we actually do that? Well, there are two particular things that we want to look at in Earth's past. One, we want to look at Earth's previous temperatures. And two, we want to look at Earth's atmospheric composition. How has the chemistry of the atmosphere changed over time? And how has that changed temperature over time? Well, believe it or not, there are actually some pretty easy but well-tested, well-accepted ways that we can do this. And why should we care about doing this? Again, because we want to know if what we're experiencing now is different than what we've experienced in the past. Is this climate change that we are currently experiencing alarming, or is it just a little blip? So how do we go about doing this? How do we go about unlocking Earth's past? Well, there's actually 3 ways that I'm going to talk about right now that we can look into the past. The first way is using what are called ice cores. The second way is looking at tree rings, and then the third way is looking at sediments. And each of these things can actually tell us a lot about previous years, either how their growing seasons were, or the composition of the atmosphere, or how much snow fell. And then we can use that data to then reconstruct previous climate. And some of the ways that we can date these ice cores, or different layers in these ice cores, or different layers in these seafloor sediments, is through the use of what's called carbon dating. And the idea behind carbon dating is when carbon at the surface is exposed to sunlight, it creates a certain isotope of carbon. And an isotope is basically a carbon atom with additional neutrons. And then when that carbon is buried beneath the surface of the Earth, it no longer has that sunlight. And therefore, it no longer gets those isotopes. And instead, those isotopes begin to decay. And so we can actually compare how many isotopes are present in something versus how many isotopes would there be if it was still up at the surface to give a relative age. Carbon dating is not a perfect science, but it is one way that we can get a peek into the past. So let me show you a few of these ways that we can look into the past. I'll talk about them really briefly, and then we'll talk about our reconstructed climate, what we know about the past. So with ice cores, basically what we do is we go out to a location that has permanent ice. So I'm talking about Antarctica. I'm talking about a location like Greenland, where there has been an ice sheet that has been present for thousands and thousands and thousands of years. And then what we do is we drill a giant tube of ice out of that ice sheet, and we pull it out. And what's actually really cool is that you can actually take a look at different layers in that ice sheet. And each of those layers indicates a certain time. And the way that this works is light layers represent summer seasons, while dark layers represent winter seasons. And a lot of this has to do with the fact that during the summertime, there's a lot more precipitation, and so that creates that light, white, fresh snow, whereas during winter time, there's less precipitation, and there's more dust, and there's more things that would darken the ice. So you usually get a lot of fresh ice during the summertime and a lot of dark, dirty ice during the wintertime. And so looking at that, we can then get a set of layers. And up here, we have these different arrows, and each one of these arrows indicates a summer. And then the dark layers represent winter, so the first pair of light and dark, that's a year. Second pair of light and dark, that's a year. Third pair of light and dark, that's a year. And so on. And we can look at a few different things. We can look at how thick each layer is. That tells us a lot about how much precipitation fell, how cold was it, how wet was it, how warm was it, and that gives us a really good idea of previous precipitation patterns. Something else that's really cool, though, is trapped in this ice are also bubbles, and inside those bubbles are ancient atmosphere. The gases of an ancient atmosphere are present in those bubbles. We can then extract the gas from those bubbles, and that can give us a really good profile of the previous atmosphere. So let's say we have a bubble here that got there 200 years ago. After looking through the layers, after doing our dating, we found out, okay, there's a bubble here, and the air inside there is 200-year-old air. We can then extract it, look at the composition of that air, and then say, okay, so 200 years ago, the atmosphere had more methane in it, or it had less methane in it, or it had more carbon dioxide or less carbon dioxide. And that could then tell us, okay, this is how these things have changed over time. Another thing that we can do is what's called dendrochronology. And in this case, what we do is we go out to some old trees and we actually cut out a small portion of the tree and we look at the rings on that tree. And these rings actually represent growing seasons. Wherever you see a really thick ring, that represents a really healthy growing season. Usually really favorable temperatures, really favorable moisture content, lots of sun, so there's lots of light. And on the other hand, a really thin layer represents a really poor growing season. These seasons can be seasons where there was very little light, or very cold temperatures, or very dry weather. And so each one of these characteristics can tell us about that particular growing season. One of the limitations about tree rings is they only tell you about the growing season. They don't tell you anything about the actual winter time, the time where the tree isn't growing. So that's a limitation. But again, we have other things that we can use in place of that. The last thing that I'll mention, and I don't have a slide for this, is seafloor sediments. There's a lot of fossils of organisms, of ocean organisms, of fish, of different types of crustaceans that sink to the bottom of the ocean, and then over time they get layered under sediment, they get buried under sediment. And we can actually use those different layers to identify how has the ocean environment changed. Another thing we can do is we can look at ratios of oxygen isotopes to tell us a lot about the past. Now, because this isn't a paleoclimatology class, I can't go too in depth onto each of these things. But just know that these are some of the tools that we have available to us to unlock our past climate. With that said, using all of the things that we've learned, using all of these different tools, tree rings, ice core samples, sediment samples, radiometric dating, we've actually been able to reconstruct past climates pretty well. And here's what we've done. What we've come across is the fact that over the last billion years, we've had 3 major glacial periods. These are periods where there was a lot of ice, where the Earth had a lot of ice on it, and so the Earth was relatively cold. These 3 glacial periods happened 700 million years ago, 300 million years ago, and 2.5 million years ago. And this most recent glacial period is called the Pleistocene epoch. And technically, we're still in it. Now, one of the things about these glacial periods, though, is they're not the same thing as you see in the movie Ice Age, where it's just everything's icy and there's no non-ice or there's no warm temperatures. Usually what we see in these glacial periods are periods of glacial advance, and then warmer periods called interglacial periods, followed by another period of glacial advance, followed by another interglacial period. And we're still technically in this most recent glacial period. And this glacial period began 2.5 million years ago. But it started with a cooling trend that happened 55 million years ago. And so the cooling that led to this current glacial period took approximately 52.5 million years. So the cooling that happened took a really long time to happen. And one of the reasons why I actually want to stress that is that transitioning from a warmer period to a colder period took millions of years. It didn't just happen abruptly. And as I mentioned previously, this current glacial period, this current quote-unquote ice age, hasn't been continuous. We've had periods of advancing glaciers, and then we've had interglacial periods, like the one that we're currently in. Now, the most recent glacial advance happened around 22,000 years ago. And during that time, polar regions were about 20 degrees cooler than they are today. Tropical regions were 5 to 10 degrees cooler than today. One of the things I actually want to point out here is usually when a climate change occurs, the tropical regions tend to get the least amount of change, while the polar regions tend to bear the brunt of it. And that's actually going to be very true when talking about modern climate change as well. You'll actually find that the polar regions have been bearing the brunt of this most recent climate change, while tropical regions, not so much. Now, during this previous glacial advance, we actually had extremely lower sea levels. And the reason why is because much of that water froze into ice. And that caused sea levels to drop. And in many cases, sea levels may have been as much as 400 feet lower. And this allowed for a land bridge called the Bering Land Bridge to develop between Asia and North America. And it's actually believed that this is one of the ways that humans actually made it to North America. They were able to cross the Bering Land Bridge and get into North America. About 14,000 years ago, we had a brief warm spell, and then a major drop in temperatures in the northern hemisphere, specifically North America and Europe, occurred around 12,700 years ago, called the Younger Dryas. The Younger Dryas. And prior to the Younger Dryas, and prior to that warm period before the Younger Dryas, this is how the Earth looked. If you take a look, there was a lot of ice. All of Canada was covered in ice. Sorry if you're from Canada, it was all covered in ice. Most of Europe was covered in ice. All of Great Britain was covered in ice. Most of Russia was covered in ice. And sea levels were substantially lower than they are today. Hence, that Bering Land Bridge was present. So obviously, the world looked really different then than it does now. The world looked really different then than it does now. And then, around 14,000 years ago, we had that nice little warming period. And then that abruptly ended with the Younger Dryas. And then, around 10,000 years ago, we got another nice little warming period. And we've been in that ever since. But one of the things I'd point out is that over the last 200 years, we've noticed a relatively sharp and abrupt increase in temperatures. In order to understand that abrupt increase in temperatures, we need to take a look at how things have changed over the past 1,000 years. So, two things are different about the past 1,000 years. Everything prior to that is relatively best guesses. There's a lot of there are errors that are present in that previous data. Now, it's still really good, really accurate stuff, but as we get closer to the present, there are more people around, there are better observations, there are better means of taking observations, and as a result, temperature observations have become more detailed and more accurate. And so when we look at this previous 1,000 years, we can actually get a really good piece of how things have looked and how things have changed. So here's how it's looked here in the Northern Hemisphere. For the most part, the previous 1,000 years have been much cooler than current conditions. There was a small warming period in the 11th to 14th century, so that was roughly from the year 1000 to 1300, where Vikings even populated Greenland. And then the Little Ice Age came, and the Little Ice Age was a cool period specifically for Europe and Greenland, and partially for North America, not the whole world experienced it. It was primarily here in the northern hemisphere. And this resulted in really harsh winters. This resulted in many famines. And this was something that actually killed off the Vikings that had lived in Greenland. This resulted in those Vikings unfortunately passing away. And Greenland is not nearly as hospitable as it used to be. And this shows us this overall trend over the previous 1,000 years. This shows us that trend. And this trend shows relatively cooler than present day averages, with a huge increase in the last 150 years. So let's actually talk about this last 150 years. Specifically, let's talk about the 19th century. Or sorry, the 20th century. I always mix that up a little bit. Then the 20th century, actually the late 19th century to the 20th century. And let's talk about what happened. So first off, now we have very accurate records. We have standardization. We have new observation techniques, new instruments. We have a lot of new things that we can use to investigate previous climates and to make current observations to develop new climate observations. And so our records over the past 100, 150 years are extremely accurate. And putting all of this together, we can actually put together a global temperature profile. And this is where the word global warming, I think, is often used when we talk about how temperatures have changed over the previous 100 to 150 years. So here's what happened. In the early 1900s, so now we're talking about 120 years ago, average temperatures began to rise. And then World War II came along. And after World War II, there was a period of great industrial growth around the entire world. And it's actually believed that during that time, there was a leveling off of temperatures and maybe even a slight cooling trend. There's some possible explanations for this, and I don't want to speculate too much here, but one of the biggest explanations is during that time, there was a lot of industrialization that led to a lot of pollution. And this was happening all around the world. And one of the key components of pollution is particulate matter. We're actually going to talk in the next lecture, in the next video, about how particulate matter, specifically aerosols, impact global temperatures. And we'll give a few examples of that. But it's actually believed that that increase in particulate matter may have resulted in a decline, a slight decline of temperatures. And then as we transition into the late 20th century, a lot of the world was realizing, okay, this stuff's really bad to breathe. We need to get it out of our atmosphere. And so clean air legislation began to get pushed forward. Particulate matter decreased in the atmosphere, and that allowed sunlight to continue its trek back down to the surface, warming us back up. That is one potential explanation, though. I don't want to go too into detail. Here's what I do want you to know. If you actually take a look at the overall trend over the past 100, 150 years, we've noticed quite a bit of warming. And in fact, temperatures now are much warmer than they have ever been. How much warmer have they become? Well, the most recent report from the Intergovernmental Panel on Climate Change, the IPCC, this is made up of the world's top climate scientists, has actually put the warming at approximately 0.85, give or take 0.2 degrees Celsius. Here's what this means. What this actually means is that we are 95% certain that the Earth has warmed somewhere between 0.65 and 1.05 degrees Celsius since 1880. So between 1880 and 2012, we have seen a temperature increase of somewhere between 0.65 to 1.05 degrees Celsius. And this give or take zero point 0.2, this is what's called the uncertainty. This takes into account all of the potential things that could be wrong with the measurements. This also takes into account statistical errors that could be present. But seeing as warming is in either scenario, either the low scenario or the high scenario, we can say with pretty decent certainty that the Earth has warmed, and pretty substantially. 0.65 degrees Celsius, that's pretty close to 1 degree Fahrenheit. 1.05 degrees Celsius is pretty close to 2 degrees Fahrenheit. So we've actually seen quite a bit of warming in the past 132 years. And one of the things I'm going to have you do this week in your module activities is you're going to be watching a documentary that shows how even a little bit of warming can create massive devastation. So this might not seem like a lot, but it's actually quite a bit. Now, in the next lecture, we're going to talk about